Hello everyone, good morning and welcome to Abhishek Jalan for you YouTube channel. My name is Abhishek Jalan and today we will explore how to effectively use GitHub Copilot through prompt engineering. So by the end of this session, you will understand how to craft better prompts, leveraging different learning techniques and optimize Copilot responses. So basically, we are going to learn how to get GitHub Copilot to give you the best possible code suggestion. So let's get started. So what exactly is prompt engineering? So in simple terms, it's about giving clear and structured inputs to an AI model so you get accurate and useful outputs. Think of it like giving directions. So if you are vague, you might not end up where you want to be. But if you are clear and specific, you can get where you want to go. For example, bad prompts like write a function. And there can be a better prompt like write a function that calculates the factorial of given number using recursion. So can you see the difference? The second prompt gives Copilot all the necessary context, like what language, what function, and what approach, like recursion in this case. Uh, Without that detail, Copilot might generate something that is completely unrelated. Now, as we have started developing some basic understanding on prompt engineering, let's understand the basic principles of prompt engineering. So, prompt engineering is basically divided on these four principles. These are also known as 4S of prompt engineering popularly. So the first principle is single, which is always focus your prompt on single well-defined task or questions. This clarity is crucial for extracting accurate and useful response from Copilot. Second principle is specific, which is ensuring that your instructions are explicit and detailed. Specificity leads to more applicable and precise code suggestions. Third principle is to keep the prompts short, which means while being specific, keep prompts concise and to the points. This balance ensures clarity without overloading Copilot and complicating the interaction. And the last principle is surround, which suggests to utilize descriptive file names and keep related files open in the editor. This provides Copilot with rich context, leading to more tailored code suggestions. These core principles lay the foundation for crafting efficient and effective prompts. So, by keeping the 4S in mind, let's dive deeper into advanced best practices that ensures each interaction with GitHub Copilot is optimized. The following advanced practices are based on the principles of 4S of prompt engineering and refine and enhance your engagement with Copilot. This ensures that the generated code is not only accurate but also perfectly aligned with your project's specific needs and context. Now let's see this in some details. Providing enough clarity means which means building on the single and specific principles. Uh, Always aim for explicitness in your prompt. For instance, a prompt like write a Python function to filter and return even numbers from a given list is both single focused and is also specific. Second best practice is to provide enough context with details. It suggests to enrich Copilot's understanding with context, following the surround principle. The more contextual information is provided, the more fitting the generated code suggestions are. For example, by adding some comments to the top of your code to give more details to what you want, you can give more context to Copilot to understand your prompt and provide better code suggestions. Another important best practice is to provide examples for learning. Using examples can clarify your requirements and your expectations, illustrating abstract concepts and making the prompts more tangible for Copilot. And the final one, assert and iterate, and it is one of the keys to unlocking GitHub Copilot's full potential. Your first prompt might not always yield the perfect code, and that's perfectly okay. If the first output is not quite what you are looking for, treat it as a step in a dialogue. Erase the suggested code, enrich your initial comment, and with added details and examples, prompt the copilot again, and you should get your desired output. Now that we have explored principles and best practices of prompt engineering, let's see how Copilot learns from your prompts. So GitHub Copilot operates based on AI models trained on vast amounts of data. To enhance its understanding of a specific code context, engineers often provide it with examples. This practice, commonly found in machine learning, led to different training approaches such as zero-shot learning. Here, GitHub Copilot generates code without any specific example while relying solely on its foundational training. For instance, suppose, uh, suppose you want to create a function to convert temperatures between Celsius and Fahrenheit. You can start by only writing a comment describing what you want, and Copilot might be able to generate the code for you based on its previous training without any other examples. Second approach is one-shot learning. Um, so with this approach, a single example is given, assisting the model uh, in generating a more context-aware response. So for example, you might provide example of a temperature conversion function and then ask Copilot to create another similar function. And then finally, a few short learning. In this method, Copilot is presented with several examples which strike a balance between zero shot predictability and the precision of fine tuning. Now let's explore the process flow for user prompts. So basically the process flow consists of two parts, the inbound flow and the outbound flow. Um so let's first try to understand the inbound flow so inbound flow kicks off with um, secure prompt transmission and context gathering. This ensures that your natural language comment is sent to GitHub Copilot server securely and confidentially, protecting sensitive information and simultaneously collecting context details, which include code before and after the cursor position, which helps it to understand the immediate context of the prompt, file name and type of the file being edited, which allows Copilot to tailor code suggestions to the specific file type. Information about adjacent and open tab. This ensures that the generated code aligns with other code segment in the same project. Information on project structure and file paths, and information on programming languages and framework. Now the second step is proxy filter. So once the context is generated and the prompt is built, it passes securely to a proxy filter hosted in the GitHub owned Microsoft Azure tenant. The proxy filter then filters traffic, blocking attempts to hack the prompt and manipulate the system into revealing the details about how the model generates code suggestions. Next step is toxicity filtering. So Copilot incorporates content filtering mechanism before proceeding with intent extraction and code generation to ensure that the generated code and responses don't include or promote hate speeches or inappropriate content or any other personal data. And the fourth step is code generation with LLMs. The filtered and analyzed prompt is passed to LLM models, which generate appropriate code suggestions. These suggestions are based on Copilot understanding of prompt and surrounding context, ensuring that generated code is relevant, functional, and aligned with project specific requirements. Now let's move to outbound flow. So outbound flow start with post processing and response validations, in which once the model produces its responses, the toxicity filter removes any harmful or offensive generated content. The proxy server then applies a final layer of check to ensure code quality, security, and ethical standards. Some of these checks include code quality and matching public code. So this matching public code check is optional, and developers can enable this check if it is needed. Otherwise, it is not enabled by default. Second check is suggestion delivery and feedback loop initiation, in which only responses that pass all filters are delivered to the user. Copilot then initiates a feedback loop based on your action to achieve the following, like grow its knowledge from accepted suggestions and learn and improve through modification and rejection of his suggestions. And the last step is to repeat for subsequent prompts, so that the whole process is repeated as you provide more prompts, with Copilot continuously handling user requests, understanding their intent, and generating code in response. Now let's discover how GitHub Copilot handles data for different environment, feature, and configuration. Data handling for GitHub Copilot editor is GitHub Copilot in the code editor does not retain any prompts, code, or any other context used for the purpose of providing suggestion to train the foundational models. It discards the prompt once the suggestion is returned. But prompts for GitHub Copilot individual plan are shared, but the subscriber can opt out of sharing this prompt with GitHub, which will otherwise be used to fine-tune GitHub's foundational model. While data handling for GitHub Copilot chat, GitHub Copilot CLI mobile, or GitHub Copilot chat on github.com, uh, GitHub Copilot retains the prompt for 28 days, although specific retention policies for GitHub Copilot chat within the code editor may vary. Multiple types of prompt are supported in these, like direct questions. So you can ask specific questions about coding concepts, libraries, or troubleshooting issues. For example, how do I implement a quick short algorithm in Python? Or why is my React component not rendering? Or maybe code related requests, like you can request code generation, modification, or explanation. For example, write a function to calculate factorial, like fix a error in my code, or explain this code snippet. You can also do open-ended queries, like you can explore coding concepts or seek general guidance by asking open-ended questions like what are the best practices for writing clean code, or how can I improve the performance of my Python application? Or you can provide more contextual prompts, like you can provide code snippets or describe specific coding scenarios to seek tailored assistance. For instance, here is a part of my code, can you suggest improvements? Or you can also ask, I am building a web application, can you help me with the authentication flow? So, as GitHub Copilot is powered by large language models, popularly known as LLMs, let's briefly explore the large language models. So, large language models are artificial intelligence models designed and trained to understand, generate, and manipulate human languages. These models are ingrained with the capability to handle a broad range of tasks involving text, all thanks to the extensive amount of text data that they are trained on. LLMs are also exposed to vast amount of text from diverse data sources. So this exposures equip them with a broad understanding of language, context, and intricacies involved in various forms of communication. LLMs also excel in generating contextually relevant and coherent text. Their ability to understand context allows them to provide meaningful contributions, be it like completing sentences, paragraphs, or even generating whole document that is contextually good. LLMs are grounded in machine learning and artificial intelligence principles. Uh, they are neural networks with millions and even billions of parameters that are fine-tuned during the training process to understand and predict text effectively. These models aren't limited to a specific type of text or languages. They can be tailored and fine-tuned to perform a specialized tasks, making them highly versatile and applicable across various domains and languages. Now let's explore the role of LLMs into GitHub Copilot and prompting. So GitHub Copilot utilizes LLMs to provide context-aware code suggestions. The LLMs consider not just the current file but also other open files and tabs in the IDE to generate accurate and relevant code completions. This dynamic approach ensures tailored suggestions, improving your productivity. Now, fine-tuning is a critical process that allow us to tailor pre-trained large language models or LLMs for a specific task or domains. Fine-tuning is also essential to adapt LLMs for a specific task, and that helps to enhance their performance. However, GitHub took a step further by using LoRa fine-tuning model. So traditional full-scale fine-tuning means to train all parts of the neural network, which can be slow and heavily reliant on the resources. But LoRa or low-rank adaptation fine-tuning is a clever alternative. It is used to make large pre-trained language models work better for a specific task without redoing all the training. So now we have reached to the end of today's session, and I hope it was informative for you. So to motivate me more for making more of such content, please subscribe to Abhishek Jalan for you YouTube channel. And if you also want to connect with me, you can do it on LinkedIn. I will also add the link for my channel and my LinkedIn profile in the description. So, thank you for your time for listening the session. Bye.